All right, bro. Good. So let me start off. Can everybody see all right? That's good? All right. So I'm Chris Lee. Welcome. It's nice to see y'all. Let me give y'all my email real quick. My pen can write. So it's Christopher dot Lee. It's like a L-E-E 02 at BCC dot CUNY. Whoops, I can't spell CUNY dot edu. All right. So if you need, like please don't hesitate. Send me a email if you guys have any questions. All right. Um while I'm going over the lesson, if you guys feel like you know the lesson already and you want to jump ahead and do the homework, go right ahead. Bring your computers, take them out. Um as far as calculators are concerned, whatever you want, grab. All right. Um Probably don't have enough time to teach y'all how to use the calculator, but you guys are welcome to go to tutoring and learn how to use it if you want to. All right. What else can I say? Oh, CPH, right, is actually down for the summer. All right. So all of tutoring is taking place in Sage Hall. Sage Hall is where the writing center is. All right. So just to let you guys know about that. And tutoring is from 1 to 6 p.m. Right? So you could literally just go there and just come here, kind of thing, you know? Um, there's tutoring in person and online. So whatever works best for you, you do. All right. Da, da, da. Let's see if I could show y'all. Or I'll give you guys a link to tutoring in an announcement. All right. But if it's your first time going to tutoring, right, you guys want to register with the page, fill it all out, correctly, and then you can log in and do your online tutoring or your in-person tutoring. All right. For online tutoring, you have to make an appointment. That way they can send you the link so you can go in to do it, right? There's a Zoom link to do the tutoring. For in-person, they like if you would make an appointment and then go, but you can just walk in if, say, it's like your own couple of minutes, you didn't have a chance to make your appointment, you can walk in, but they do like it if you could make an appointment before you go. All right. Questions on that? Everybody's like familiar with it, right? So for me, I'm gonna be there Monday and Tuesday, 1 to 3. Yeah. But there'll be other people there too, the whole time. Monday through Thursday, by the way, Monday through Thursday. All right. Oops. All right. So math 30. All right. Let's talk about this a little bit. So what is math 30? What we're going to be doing, we're going to be studying the relationship between functions and their graphs, essentially. That's the whole class in a nutshell. All right. Let me show y'all the syllabus real quick. Yeah, I don't know. Right now I see 130, and before I was seeing 131. Matter of fact, hold on. When I was on this computer, it was saying 131. So let me refresh this page and see if it still says that. Because I'm over here confused myself. You know? What's up, man? How you doing? Good, 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 good. Yeah, man. It's all right. It's all right. Text me. Text me. All right. Yeah. Should be in this class, man. But sorry. Let me see real quick. I know I'm not bugging. Yeah, see, this joint says 131 now. So I don't know. A couple weeks ago it said 130, now it's saying 131. I don't know. Anyway, let's look at the syllabus real quick, right? I'm gonna show y'all organically like how to get to it. All right. So you go to the BCC website, you go right here to where it says academics. All right. And you go to where it says academic departments. And then you just scroll down to where it says math and computer science. Right here. And then you want to go to where it says degree programs and courses. And then you kind of just scroll down to where it says Math 30 pre-calc right here. And then right here is the syllabus. There's also the review sheet for the final, but yeah, I don't need that for a couple of weeks. All right. So here we go. This is the syllabus right here. All right. So, the prerequisites of the class is Math 28. Yay. All right. This is your textbook right here in case anybody likes to read. All right. Up to you. All right. A little bit about the class. I told you we're going to be studying the relationship between functions and their graphs, right? And some other details. All right. Just fulfilling pathway core B, all that good stuff. Yada, yada, yada. Y'all can read this on when y'all have time. All right. Academic integrity, don't cheat, but there's nothing wrong with asking for help. All right. If anybody here is allowed accommodations, please let me know. Right. If you don't know how to get accommodations, this is how. All right. You can go to Low Hall 211, right? Or you can call them or you can shoot them an email and they'll help you set up accommodations in case you want. Accommodations are things like extra time, things like say you want to take your test but be in like a quiet room or something, like things like that. All right. And this works for all your classes too, not just this class. But there you go. That's the information. This is what we're gonna attempt to go through. OMG, it's a lot of information. I'm not gonna lie, it's a lot. All right, but we can do it though. All right, it's not so bad. Questions on this? Go ahead. Yeah, we gonna do the same thing. We're gonna do the same thing. I mean, we're gonna have to like trim the fat though. We can't do like every topic. But we gonna do what we can. You know. Yeah. I'm sorry. 2 weeks at a time. 2 weeks at a time. Yeah. Exactly. Yeah, exactly. Or at least we're gonna attempt to do that. I don't know. Yeah. Yeah, we gonna attempt to do that, you know? Maybe not today, but definitely tomorrow. Yeah. So that's that. While I'm on the internet right here. So for tutoring, it's WC Online, right? I'm gonna send y'all an announcement with this link right here. But this is the main website for tutoring. You just come right here where it says register for an account. If it's your first time, I feel like everybody here is familiar with tutoring, so it might not be your first time. So you guys already have your logins and everything. But if it's your first time, click right here, register for an account, fill it out, and then that's it. All right. Again, like if you're gonna do the tutoring online, you have to make the appointment, right? And you just click it right here, right? This is for the online tutoring. Um, July, yeah. That's for the online tutoring. If you want to go in person, you can just walk in, but they ask that you make an appointment. So this is how you'd make the appointment right here. And that's it. Questions on that so far? We good? All right, all right. And there's something else. Oh, let's talk about web work. Everybody here is familiar with web work? A little bit? All right. So all I did was just Google BCC and web work, right? You just click on right here where it says web work. You have a lot of stuff to go through, all right? If you're on a Mac, right, press Command and F. If you're on a PC, you can do Control and F, right? That makes this little search finder thing come up, right? And then you can just type in like the class instead of having to scroll through everything, right? So first thing you do is the year. So 2025, right? And then it highlights all of the 2025 classes, right? Hit the space. This is what semester? Summer, right? So you just write summer, right? Those are all the summer classes, right? And then my last name is Lee, right there, Math 30. Boom. So this is how you get to your homework, all right? Your username, everybody, your username and password is your first name and then your last name as one word. No space, no capital letters, none of that. Just one word. That's your username. What? Is this the website? No, no. This is on WebWork. This is a separate website. Yeah. So Google BCC and WebWork, or look at what's that thing called again? Brightspace, right? I mean, I gave you an announcement about this already. It was free. Yeah, yeah, yeah. Huh? Yeah, yeah, yeah. That email is from Brightspace. So if you guys go into Brightspace, then you guys can see it. You know how to get into Brightspace? Okay. I know because of that thing. So yeah, last when was it? Tuesday that just passed, right? CUNY first, CUNY Central, excuse me, they blocked everybody until we change our passwords and we do two-factor authentication. So we have to set that up, right? I know that last week, Roscoe, yeah, yeah, yeah. Yeah, I understand. I understand. Last week, I want to say IT was open till 9 p.m. to help everybody fix it. I don't know if they're open today till 9 p.m. as well, but definitely they're open up until 5 p.m. every day, you know? So I understand if you guys have to go and get it. It was open just now? All right. Yeah, yeah. So if anybody needs to go, I mean, like next week, they're not opening until 9 p.m. They're gonna close at 5. But if anybody needs to go like today or something, I completely understand. Again, I'm recording this, so if you want to fix the IT issue, go fix it and come back. You know, like so you guys can watch whatever you missed. All right. Yeah, so if you want to go to IT and fix it right now, you can. There's no problem. All right. Yeah, so if you go into Brightspace, you'll see the announcements that I made, right? Like I gave you a little welcome. I gave you the link, this particular link on how to get to the homework, right? Along with instructions of how to type in your username and password, right? So one word, no capital, if you guys have cell phones, you could try it right now, or if you want to try it on your computers, go ahead. All right. So if you're going through Google, it's BCC and WC online, or if you go through Brightspace, the link is there already. Just click it. All right. Questions on this? Go ahead. Yeah, yeah. You could just go through Google. Somebody else had a question. I heard a voice, but I don't see. The password is gonna be your first name and then your last name as one word, right? No capital letters, like all lowercase. Yeah, yeah. All right. Same thing. Password, username, same thing. All right. It's on Brightspace. Yeah, yeah, yeah. But yeah, it's the same link. This particular link is on Brightspace. Yeah. Um, it might be in your email too, because I think every time I post something, you get an email from it. Yeah, so you might today. I get them like 24 hours then. Yeah. All right. So questions, anybody? We all good? Good? All right. Your first name and then your last name. Yeah. No space, no dot, just one word, no capital letters. Right? No, same thing. Username and password, same thing. Yeah. Yes, yes, you can. Yeah, it's fine. I'm recording this, so you'll it's not a problem. Yeah, yeah. Okay, no problem, no problem. If anybody else needs to get it fixed, go right ahead. I understand. All right. You just type in the answers and that's it. Yeah. The final answer. Yeah. On web work, I'm more interested in all of you getting 100. All right. I don't care how many times you do the question, like I don't care if like you ask for help on one and then you do the rest of the homework on your own, whatever. All right. I need to know all those details. I just want you to get 100. All right, just give me 100. That's all. All right. Um, ba ba ba. So I'm trying to do a test every 3 weeks. So that would be like every 6 days in this summer session. So like next week, Wednesday, I'm thinking about our first test. All right, or at least I'm aiming for that. Da, da, da. Give me 1 second because I one of the announcements I need to show you guys. So my new thing now is every time I go to CUNY first, it's like wrong password. Gotta do it again. Oh Lord. Go ahead. Every day. Now it's not due like tomorrow or nothing, but you should aim to do it like tomorrow, you know? If um if it goes over into the weekend, that's fine. Well, I understand that that could happen too. That's annoying. I don't know why they think we're going to hack into each other's CUNY first or whatever. Somebody did that? Oh my Lord. What is there to get out of CUNY first? That's in CUNY first? Damn. Yeah. Damn. Damn. Man. So real quick, just want to show y'all the grade breakdown. And we could talk about that. So yeah, that's my name, that's my email, right? So your final exam is going to be 33% of your grade. Your in-class tests that we're going to have, they're going to be 30% overall, all right? And then your homework will be worth 37%. Questions, anybody? You good? That's it. That's all I had to say about the syllabus and all that. So let's jump into this. Math 30. Let's see what we're getting into, right? So our first topic is we're going to be determining whether a relation represents a function. All right. So a relation is a set of ordered pairs. All right. So the set of the first components of each ordered pair is called the domain, and the set of the second components of each ordered pair is called the range. All right. Consider the following set of ordered pairs. The first numbers in each pair are the first five natural numbers. Natural numbers, 1, 2, 3, 4, 5, 6, those natural numbers, all right? The second number in each pair is twice that of the first. So 1 times 2, 2, 2 times 2, 4, etc. Right? So right here, we have a set of numbers. We know this is a set because of the curly braces that are on the end right there. And within each set, we have another set of numbers, right? A tuple, right? Fixed, it's closed. All right, try tomorrow. No problem, no problem, no problem. All right. So that's a set of numbers, right? The domain in this set is the natural numbers 1, 2, 3, 4, 5. That's these beginning numbers here. And the range in the set is the second numbers next to it. The 2, 4, 6, 8, 10. Make sense? All right, cool. So note that each value in the domain is also known as an input value, X, right? Or the independent variable, right? And is often labeled as lowercase letter x. Each value in the range is also known as the output value or dependent variable and is often labeled as lowercase letter y, right? So a function, f, is a relation that assigns a single value in the range to each value in the domain. In other words, no x values are repeated, right? So for our example, for our example, that relates the first five natural numbers to numbers double their values. This relation is a function because each element in the domain, 1, 2, 3, 4, 5, is paired with exactly one element in the range, 2, 4, 6, 8, 10. All right. So long story short, right? You see a relation. If you see one X that's going to two different ranges, two different Ys, not a function. All right. You'll see a lot of examples like that in the homework. All right. So now let's consider the set of ordered pairs that relates the terms even and odd to the first five natural numbers. It would appear as odd, comma 1, even, comma 2, odd, comma 3, even, comma 4, etc. Right? Notice that each element in the domain is even or odd, right? Is not paired with exactly one element in the range, which is 1, 2, 3, 4, 5. So for example, the term odd corresponds to three values in the range, 1, 3, and 5. And the term even corresponds to two values in the range, 2 and 4. This violates the definition of a function, so this relation is not a function, right? Go ahead. Got you, got you. Look. So you see how I have odd right here and it's going to 1. Then I have odd right here again and it's going to 3. I don't even have to do the other one, right? Just that in itself violates the definition of a function. One x value cannot go to multiple y values. All right. So it's that simple. In the first relation, none of these x's repeated, you know, and they all had their own unique y that they was going to. So it's straight. That's a function. All right. Questions on that? Anyone? Hmm? Let's see. Oh, sorry, go ahead. Mhm. It wouldn't be a function. Yeah, because that's like the same X value going to two different Y values. Yeah. The bottom one is not. The top one was. Yeah. In the Y it is, right? In the range it is, but not in the domain. If the domain has one X value that goes to two different Y values, two different ranges, it's not a function. Right? Don't worry, you're gonna see some practice with it. You're gonna see some practice with it. Okay. I'm a fan of pictures, so let's take a look. All right. So in this figure, right, we're going to compare relations and their functions and not functions, all right? So take a look at this. Relation is a function. We have the inputs P, Q, and R, right? And each one of those goes to its own output, right? It can repeat, right? Like two different X's can go to the same Y. That's a function. But the same X can't go to two different Y's. That's not a function. All right. So like that's what is being described in this first image right here. Right? I have three inputs, right? They're all different, right? And they're going to an output, right? Now, two of them are going to the same output. That's okay. That's okay. All right. But if they were going to, if two of them, not two of them, if one of them was going to two different outputs, that's not okay. Like this last one over here, right? You see where I have the P and the Q? And then the Q is going to two different outputs. It's going to the Y and the Z. That's not a function, right?
So if this was a graph, would it be a function, but and the X not function two buyers and they connect vertical line?
It fails the vertical line test. Very good.
Yeah, so
Yes.
So there's no like, why, and then you put a B.
Right.
Because you buy it, got all, right?
Exactly. We're actually gonna talk about that a little bit later. But yeah. Yeah. That's it. Right. In the middle, right? This relation is a function when you have every X has its own unique Y, right? In fact, we're going to even take that up a notch. That's called a one-to-one function, right? When every X has their own Y that they go to, right? Every input has their own unique output, right? So figure one, this relation is a function because each input is associated with a single output. Note that inputs Q and R both give output N, right? This relation is also a function, right? In this case, each input, is associated with a single output, right? That's for part B, the middle one. For part C, this relation is not a function because input Q is associated with two different outputs. All right. That's it. Questions on this? No? In the homework, it'll make more sense. Promise. Yeah. Because this is more theoretical, you know? But when you see the homework questions, it'll be like, yeah, I know. That one is function, that's not, you know? Want to give you a little definition real quick. So a function is a relation in which each possible input value leads to exactly one output value. We say the output is a function of the input. All right. The input values make up the domain and the output values make up the range. All right. All right. This next part is really important. I'm about to give y'all the sauce right now. All right. It's a little how-to. So given a relationship between two quantities, right? How do you determine whether the relationship is a function? This is how, right? First, you want to identify the input values, the X values, right? 2, you want to identify the output values, the range, right? And 3, if each input value leads to only one output value, classify the relationship as a function. If any input value leads to 2 or more outputs, do not classify the relationship as a function. That's simple. All right. Let's look at an example real quick. All right. This going to bring it all home for us, right? So we want to determine if menu prices listed, right, are functions, right? So the coffee shop, right, shown in figure 2, this is figure 2, consists of items and their prices. Question A, right? Is price a function of the item? Right? Is price a function of the item? And then question B, reverse, is the item a function of the price? What do we think? It's not an A and B question. Like both of them are two separate questions. You said go back up, right? Let me see the question like that. Okay. Yes to A? It is yes. All right. So price is a function of the item. So I have 3 different items, and each one of them goes to its own price. It's okay if the price is repeated, right? But what about the reverse? What about B? It's not, right? Why? I have one price that goes to 2 different items, right? In the reverse. Make sense? All right, let's look at some more stuff then. Let's look at another example. For this example, it says determine if the class grade rules are functions, right? So in a particular math class, the overall percent grade corresponds to a grade point average. Is grade point average a function of the percent grade? And that's the first question. Second question, is a percent grade a function of the grade point average, right? So same thing, we're going from one to the other, right? Is percent grade, right, a function of the grade, and is the grade a function of the percent? What do we think? Hmm? Okay. Why? Very good. Like that. The only issue that I have with this is the range. You see right here how I have the percent grades gives me a range, right? Because of that, the grade point cannot be a function of the percent because I'm getting like 2 different Y values for one input. Right. Right. For the second question. First question is fine. For the second question. So, right?
Isso é pode comer os ossos.
I know, I know. All right, here's another example. All right. So we have a table here, right? And it lists the 5 greatest baseball players of all time in ranking order. All right. So Babe Ruth 1, Willie Mays 2, Ty Cobb 3, Walter Johnson 4, Hank Aaron 5, right? Is the rank a function of the player name?
Yes.
Good. Is the player name a function of the rank?
Yeah.
Good. All right. So we getting it. We getting it. But I feel you though, it is tricky. All right. Questions on this so far though? This idea of what is a function, what is not a function.
So
Mhm.
I thought it was just one X, like say for
Mhm.
can't have two different values,
Exactly.
but it's like for the output. Two inputs can't have the same output. Like say two and
No, no,
four.
2 inputs can have the same output.
But
Yeah. Yeah. But the first one you said yes. Yeah. All right, let's switch it up a little bit. Let's talk about function notation. Good stuff. Got to build a vocabulary a little bit before we jump in, right? So using function notation. Once we determine that a relationship is a function, we need to display and define the function relationships so that we can understand and use them. And sometimes also so that we can program them into computers, right? There are various ways of representing functions. A standard function notation is one representation that facilitates working with functions. All right. Excuse me. To represent height is a function of age, right? We start by identifying the descriptive variable h for height and a for age. The letters F, G, and H are often used, lowercase by the way, are often used to represent functions, just as we use X, Y, and Z to represent numbers, and A, B, and C to represent sets, capitals. So we use our capital letters for sets, lowercase letters for functions. All right. So H is f of a, right? We name the function f, and the height is a function of age. Or you can also say is h is equal to f of a, right here in the second line, right? So we use the parentheses to indicate the function input, right? So I'm inputting a, age, into the function to get out my answer, which is height. All right. And then f of a right here, we name the function f. The expression is read as f of a. All right. So anytime you see something that looks like this, right? The f with the parentheses and then the a is read as f of a. The whatever's in the parentheses, that's my input. That's what I'm gonna plug into the function. All right. Questions on that? Good. All right. Y'all remember this from Math 28? All right. All right, cool. All right. So remember, we can use any letter to name the function, right? The notation h of a shows us that h depends on a, right? A value a must be must be put into the function h to get the result. The parentheses indicates that age is input into the function. They do not indicate multiplication. All right. So when you see f parentheses a, that doesn't mean f times a, right? So that's what that's saying. We can also give an algebraic expression as the input of a function. So for example, f of a plus b, right, means first add a and b, and the result is the input of the function f. This operation must be performed, right, in order to obtain the correct result. All right. So now we're getting a little tricky. Give y'all a little bit of definitions real quick. Function notation right here. All right. So the notation y equals f of x defines a function named f this is read as y is a function of x. The letter x represents the input value or the independent variable. The letter y or f of x represents the output value or the dependent variable. Right? Nothing new here, right? That's what I'm saying. If some of y'all bored, go ahead, do y'all homework. I understand. I get it. Mhm. Let's take a look at an example, right? So using function notation for days in a month, right? Use function notation to represent a function whose input is the name of the month and output is the number of days in the month, right? Assume that the domain does not include leap years. All right. So what do we think? So I want my function to give me the days, right? So that's my answer, right? This would be like my y, right? And I'm looking for my f of x here, right? So my input is the name of the month, right? So this would be what? F of whatever how you spell name again? Name, right? The name of the month. And that's it, right? So I plug in the name of the month, I get out the number of days that it has. That's a function. Questions on that? All right. Might look a little simple. I know. I know. I know. I don't want to do any month examples because, be honest with y'all, I don't know how many days are in each month. I think June got 30, right? Let's do June. Just because today's the 30th. So 30 is equal to the function of June, for example. All right. They say tomorrow's July, so yeah. I think July is 31st day, 31 days. I don't remember. It's 31? All right. I was about to ask Alexa. I don't even know. So I just want to make a little special note real quick, right? A little analysis, right? So note that the inputs, right, to a function do not have to be numbers, right? Function inputs can be names of people, labels of geometric objects, or any other element that determines some kind of output, right? However, most of the functions we'll work with in the book will have numbers as inputs and outputs, right? So we're not going to be working with like statements, we're going to work with numbers, right? But just to make you understand it, that's why I do it like this. That being said, let's look at another example. So this is interpreting function notation. So a function n is equal to f of y gives the number of police officers, right? So n is the number of police officers in a town, no, in a town in a year, particular year, right? So y is the year. So what does f of 2005 equal 300 represent? Is the year, and the 300 is what? Number of police officers. That's it. All right. So my input is the year. My output is the number of police officers that were working that year. All right. Questions on that? Good. All right. So if this was like X and Y, right? I'm telling you that X would be like the year. In this case, 2005. And then Y would be the N or the number of police. And that would be the 300. Mhm.
So X holds. Like X not hold the data and Y in the representation of that data. Like with that, with, they're not special, like,
Yeah, yeah.
and Y would be each individual part. In other words, the data.
Could be.
Like you said, oh, like, pick a part with that.
Right.
The data would be your X, and if you pick a card, that would be Y. Now,
I could think of it like that. Yeah. That makes sense. Yeah.
I see it because here,
Yeah.
like, here's the year.
Right.
The year 2005 is one in control.
Mm-hmm.
So we.
That's the dependent variable, right?
Yeah.
Right.
And the guy gets.
Oh, excuse me, the independent variable. I meant to say, I'm sorry. All right.
The year doesn't change.
Mm.
But if I say,
Right.
you get the name for resources, that changes.
Right. Yeah. Mhm.
You know?
Now you're thinking like in Excel terms. I like that. All right. Questions on this, anybody? Good? All right. Let's look at another example. So in this example, right, use function notation to express the weight of a pig in pounds as the function of its age in days. So tell me what to write. So what's my input? It'd be days, right? Good. The input would be the days. Or D. And what would be my output? The weight in pounds. Very good. All right. So if I had F of days, that would give me the weights in pounds. That's simple. Questions on this? All right. Just trying to make sure y'all understand. Mm-hmm.
We can put, big basically out.
It is. It's the exact same thing.
What's,
Mhm. Yeah.
what's instead, so on.
Yeah.
You know that, it's good.
Gives you that output. Yep. That's the exact same thing. Mhm. All right, let's make a little special note. So instead of a notation such as y equals f of x, right, could we use the same symbol for the output as for the function, such as y equals y of x, meaning that y is a function of x? Yes, you can, right? This is often done, especially in applied subjects that use higher math, such as physics and engineering. However, in exploring math itself, right, we like to maintain a distinction between a function such as f, which is a rule or procedure, right? And the output y we get by applying f to a particular input x. This is why we usually use notation such as y equals f of x or P equals W of D and so on and so forth, right? I believe that's power equals work times whatever. When you take physics, you'll learn that. All right. Questions on this? Good. All right. Sounds good. Sounds good. Sounds good. Let's look at the table real quick. All right. Ooh, my mistake. Sorry about that. All right, representing functions using tables. So a common method of representing functions is in the form of a table. The table rows or columns display the corresponding input and output values. In some cases, these values represent all we know about the relationship. Other times, the table provides a few select examples from a more complete relationship. All right, so table 3 lists the input number of each month. January is 1, February is 2, and so on, and the output value of the number of days in that month. So this information represents all we know about the months and days for a given year. That is not a leap year. So note that in this table, we define a day or days in a month function, f, where D is equal to f of m, right? Identifies the months by an integer rather than by a name. So we have the month numbers here, 1, 2, 3, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we have the days in each month. I should really study this. I didn't know this. Oh, okay. My fault. I digress. Anyway, so table 4 defines a function Q is equal to G of n. Remember, this notation tells us that G is the name of the function that takes the input n and gives the output Q. All right. So this is an example of table data that we can represent as a function. All right. Good stuff, good stuff, good stuff. So table 4 defines a function Q is equal to G of n. Remember, this notation tells us that G is the name of a function that takes the input n and gives the output as Q. All right. Here's another table. All right. And as you can see right here, I have two different x's that go to the same y value. All right. So that's legal. Right. You can have two different x's go to the same y value. That's a function. Let's take a look at another kind of table. So this would be our table 5. Displays the age of children in years and their corresponding heights. This table displays just some of the data available for the heights and ages of children. We can see right away that this table does not represent a function because the same input value for 5 has two different output values of 40 inches and 42 inches. All right. There you go. Go ahead. Right. Right. Yeah. In the table, yes. Yeah. Mhm. Any other questions? Good. All right, let me drop y'all with the sauce real quick. I'm about to give y'all that good right now. This little how-to. All right. So given a table of inputs and output values, determine whether the table represents a function. This is how you do it. First, you want to identify the input and the output values. And then 2, you want to check to see that each input value is paired with only one output value, right? If so, the table represents a function, right? If not, it's not a function. That's simple. All right. That's a sauce right there. All right. Let's look at an example real quick.
Yeah. Said ten.
Yeah.
So like those were like, I said like five,
Mhm. Yeah.
Like I asked, and I said, oh, how many multiples do you have in diagonal 5?
Mm-hmm.
You say 40.
Yeah,
Actually, yeah, no, we want to see like a 5, 6, 42.
yeah, exactly. That wouldn't be a function.
That should be technically possible.
Right,
If you're only confident that we're 40 in there. it's not
exactly,
72.
exactly. That's it right there. How about this one real quick? Let's look at this example. Right, so identifying tables that represent functions, right? So which table? This one, this top one is 6, right? The next one I'm gonna post up is 7 and 8, right? Which one represents a function? Let me get the other table real quick. 1 second. Oh, let me make it a little bit bigger. I'm sorry. Huh? That's a function right there? Good. This one? Good. How about this one? How about this one?
No.
7 is not a function? Good.
6.
8, right.
Okay.
8 is not a function. Good. I'm impressed. I'm not gonna lie. Have fun with your homework. That's all you're gonna be doing on the homework. Just yes, no, yes, no, yes, no. Huh? Yeah. Bad part is that you have unlimited attempts, so if you get it wrong, it's just the other answer. I feel you. I feel you. All right, so we got our solution right here. Table 6 and 7 define functions, right? In both, each input value corresponds to exactly one output value. Table 8 does not define a function because the input value of 5 corresponds to 2 different output values. So when a table represents a function, corresponding inputs and output values can also be specified using function notation. All right. And then the function represented in table 6 can be represented by writing f of 2 is equal to 1, f of 5 is equal to 3, and f of 8 is equal to 6. Similarly, the statements g of -3 is equal to 5, g of 0 is equal to 1, and g of 4 is equal to 5 represents the function in table 7. Table 8 cannot be expressed in a similar way because it does not represent a function. Right? Just giving y'all some little details with it. All right. Let's take it up a notch real quick. Damn. Table 9, function or not a function? Okay. All right, I feel like y'all get it. It's like half your homework right there. So let's take it up a notch. So we want to be finding input and output values of a function. So when we know an input value and want to determine the corresponding output value of a function, we evaluate the function. So evaluating will always produce one result because each input value of a function corresponds to exactly one output value. All right. When we know an output value and want to determine the input values that would produce that output value, we set the output equal to the function's formula and solve for the input. Solving can produce more than one solution because different input values can produce the same output value, right? So evaluating a function in algebraic form. So when we have a function in formula form, it is usually a simple matter to evaluate the function. For example, the function f of x is equal to 5 minus 3x squared can be evaluated by squaring the input value, multiplying it by 3, and then subtracting the product from 5. Real simple, all right? This I know we did before. So I'm just going to give y'all the sauce, and then we'll look at a quick example. All right. Little how-to. So given the formula for a function, let's evaluate, right? And how do you do that? Step 1, substitute the input variable in the formula with the value provided. And step 2, calculate the result. That's it. All right. Plug it in, little math, give me the answer. That's it. All right. All right. Y'all probably seen this in 28 also, if I'm not mistaken. So evaluating functions at specific values. So we want to evaluate f of x, which is equal to x squared plus 3x minus 4 at 2, at a plus h, and now at f of a plus h minus f of a divided by h. Let's take this step by step. So step by step, right? So I'm gonna look at a real quick. So they want to know what is 2, right? So essentially what they're asking is what is f of 2? That's what they're asking. So you're going to take that 2 and you're going to plug it in everywhere you see the x, all right? So this is going to become what? This is going to become 2 squared plus 3 times 2 minus 4. Little math. What is that? 4 plus 6 minus 4. Let's call that 6. Questions on that, or are we good? Good? All right, same old, right? But check this out, though. Check this out. Let me get a color. All right. For B, they want you to plug in A. So what are they asking you for? They're asking you for f of A. Right? So everywhere I see x, go ahead.
A squared plus 3a minus 4.
Very good. And that's my answer right there. Everywhere I see x, I plug in for A. All right. Questions? Are we good? Good? All right, let me get another color real quick. Hold up. It's my alma mater's color right here. I got the lavender right here, you know? All right, so they want to know what is f of A plus H. What do you think I'm going to do here? Plug it in, right? Plug it in. So this is going to be A plus H squared plus 3 times A plus H minus 4. And what do I have to do after this? Solve it, right? So help me solve this. What's the first part? A squared plus H, very good, plus, good, keep going, good, plus 3H minus 4, all right? Questions from anybody on how we did that? Go ahead. So you see right here where we have A plus H squared, right? Think of it as this. It's A plus H times A plus H. And then you just FOIL it, and that's where it comes from, right? But how she did it over here, do you remember this? A plus B squared is equal to A squared plus 2AB plus B squared. That's one of those fundamental formulas from 28. Whichever works for you. If you don't remember the formula and you want to put them together and distribute it out, go right ahead. Right? As long as you give me the right answer, I really don't care. All right. But for me, I would be using my shortcut because I like shortcuts.
The A together,
What do you mean?
because you got A squared by times A with A.
A times A.
Yeah.
Yeah.
Yeah, so we're adding H plus H to get to A.
So when you FOIL it out, the first one is going to be A times A, which is A squared. The next one will be A times H, which is AH. And in the middle will be H times A, which is HA. You can add those together to get 2AH. And that's how you get that. And the last one is H times H. Anyway, let's combine like terms, all right? So give me the answer right now. So a squared plus what? Two AH, okay. Plus H squared plus 3A plus 3H minus 4. There's no like terms there. All right. So that's it. But if there was a like term, you would just add them together, blah, blah, blah. All right. So we good? All right, let's look at D. D looks hella crazy, right? It's not though, I promise. So they want f of A plus H minus f of A all divided by H. You know what f of A plus H is, you just did it, right? So that's what? A squared plus 2AH plus H squared plus 3A plus 3H minus 4 minus, now look, I'm putting this in parentheses, f of A. We just did f of A. It's in orange right there, right? So that's going to be the A squared plus 3A. Whoops, I didn't mean to do that. Minus 4, right? All of this divided by H, right? Next, what am I going to do? Okay. Simplify. Help me. Okay. Yeah. But there's something I want you to tell me to do. Starts with a D. Not divide. Distribute, right? What am I going to distribute? Close.
I wouldn't give people solve it, because this.
We're gonna solve it?
Solve the top.
Mhm. That's what I want you to do, solve the top. All right. All right, it's a negative. Distribute that. All right. And then now let's look at what I have. I have A squared plus 2AH plus H squared plus 3A plus 3H minus 4 minus A squared minus 3A plus 4. Right? All of that over H. Let me get another color real quick. So now I want to combine like terms, right? So look, I got positive A squared here, negative A squared, that's gone. All right, I got positive 3A here, negative 3A, that's gone. I got negative 4 here, positive 4 here, that's gone. All right, so let's look at what I'm left with. Oops. Let's look at what I'm left with. So this is 2AH plus H squared plus 3H all divided by H. Let's do, right, greatest common factor on the top. Let's look at what we have. I have H times 2A plus H plus 3, all divided by H. These will cancel. Final answer. Plus 3. There we go. And that's it. Questions on this? Huh? This was fun though, right? This is actually a really, 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 really important formula. You're going to see it again in calculus. This formula. All right. So we good? No questions? All right, send your homework. Yeah, I probably don't need this example, but just humor me to make me feel good. So we evaluating functions. So given that h of p is equal to p squared plus 2p, evaluate h of 4. Tell me what to do real quick. Very good, right? This is going to be 4 squared plus 2 times 4. Little math. What's that? 16 plus 8? What's that? 24? All right. Questions on this? We good? All right. Too easy?
Yeah.
All right. That's all right. I like easy. Yeah. Oh yeah. I mean, but y'all get the gist, so I don't need to go that deep, right?
Yeah.
Mhm. Yeah, go ahead. Yeah, go ahead. Are they? Yeah.
For me, at least.
Yeah. Okay.
They're not really-
Yeah, most definitely. Most definitely. Yeah. Yeah. Or you can order tutoring in case you look at it after class and we're not in session, you know. Yeah, that's fine too. As long as you get a homework, 100 on the homework, I really don't care. You know, like how you do it. A little bit harder. Tell me what to do. So g of 5. So this is going to be equal to the square root of 5 minus 4. Y'all got to help me. I'm bad at math. What's 5 minus 4 again? 1. All right, square root of 1. Yeah. And what's square root of 1? Very good. See, y'all good. Y'all gonna pass. Y'all good. Y'all know everything. That's what's up. That's what's up. All right, let's move on. I feel like y'all get the idea. So I want to look at evaluating functions expressed in formulas. All right. Some functions are defined by mathematical rules or procedures expressed in equation form. If it is possible to express the function output with a function involving the input quantity, then we can define a function in algebraic form. So, for example, the equation 2n plus 6p equals 12 expresses a functional relationship between n and p. We can rewrite it to decide if p is a function of n. All right. Let me just give y'all a little how-to real quick. You see what we're getting into. So given a function in equation form, right, it's algebraic form. So solve the equation to isolate the output variable on one side of the equal sign with the other side as an expression that involves only the input variable. Use all the usual algebraic methods for solving equations such as adding or subtracting the same quantity to or from both sides, or multiplying or dividing both sides of the equation by the same quantity, right? Solve for the output variable. That's what it's trying to say. That's simple. All right. I think we did this before. So let's check this out. So I want to express the relationship 2n plus 6p equals 12 as a function p equal to f of n if possible, right? Long story short, Solve for P. That's all it's saying. Tell me what to do. I got 2n plus 6p is equal to 12. Solve for P. What should I do? I'm sorry? Not not quite 0, but I want P to be by itself on one side. Yeah. Mhm. Multiply by 12? Move the 2n, right? So how do I move the 2n?
Subtract.
Good. Subtract 2n. Now what you do to one side, you have to do to the other, right? So now what I got? I got 6p is equal to, let's say, negative 2n plus 12. What should I do after that? Divide by 6, right? Everybody gets divided by 6. And then let's simplify this down. So P is equal to, what's this? Negative 1/3 n plus 2, right? And that's it. Remember how to do this, right? Nothing crazy here. Just solve for the variable that they're asking you for. That's all. Hmm? I know some of y'all look disappointed, like this is math 30. Like, dang, like that's what I'm saying. If you feel like you got it, take out your phone, your computer, just knock out the homework. It's all good. No pressure. So I want to make a special note real quick. So it is important to note that not every relationship expressed, excuse me, by an equation can also be expressed as a function as a function with the formula. Sorry about that. So here we go. Let's look at this example. So, sorry. So expressing the equation of a circle as a function. So does the equation x squared plus y squared equal 1 represent a function with x as the input and y as the output? If so, express the relationship as a function of y equals f of x. Blah, blah, blah. Solve for y. That's all that means. All right? So let's do it. I got x squared. I'm going to do this in black. I got x squared plus y squared is equal to 1. Solve for y. Help me out. How do I do this? Subtract x squared. Very good. What I do to one side, I got to do to the other. So now I got y squared is equal to negative x squared plus 1. What should I do after that? What is it? Square root both sides, right? What I do to one side, I got to do to the other. So now what do I have? Somebody tell me the answer. Equals. No. That's part of it. All right, plus or minus square root negative x squared plus 1. Right? There's two answers there. Right? So long story short, is this a function? Y. Two Y answers. Very good. All right. And that's it. That's the trick right there. That's the trick right there. Let me see if y'all really got this. Let me see if y'all really got this. Oh, snap. Here we go. So if x is minus 8y cubed is equal to 0, express y as a function of x. So help me solve for y here. Go ahead. What should I do?
Where's the, by itself?
Very good. What you do to one side, you do to the other. So now I have negative 8y cubed is equal to negative x. What should I do after that? Or before that? Divide by negative 8, right? What you do to one side, you have to do to the other, right? A negative divided by negative is a, all right, so y cubed is equal to x over 8. And how do I get rid of that cubed? Cube root. Very good. I'm going to cube root this, and what I do to one side, I do to the other, right? So now what do I have? I have y equals what?
With two. Excellent.
Very good. So cube root of x over 2. All right. So that's cube root of 8. Over 2. Yeah. So 2 times 2, 4, 4 times 2, 8. That's how, yeah. Is this a function? Very good. All right, because I have one y output. All right. Tricky, right? I'll see that on the homework, don't worry. But just to elaborate on this situation just a little bit, give y'all a little special note. So are there relationships expressed by an equation that do represent a function, but which still cannot be represented by an algebraic formula? Yes, this can happen. So for example, given the equation x equals y plus 2 to the y power, if we want to express y as a function of x, there is no simple algebraic formula involving only the x that equals y. However, each x does determine a unique value for y, and there are mathematical procedures by which y can be found to any desired accuracy. In this case, we say that the equation gives an implicit or implied rule for y as a function of x, even though the formula cannot be written explicitly. All right? So long story short, that wouldn't be a function. No? Just letting y'all know. No, that's not on your homework. It's just for your knowledge. Right?
Why would it be a function?
Because you can't solve for y. For x, it would be though, if it was the reverse. Huh?
That's the output.
Mm-hmm.
And get the output being on the input.
Right. Yeah. All right, let's look at this one real quick. So this is evaluating a function given in tabular form. Oh, this is my favorite right here. So as we saw above, we can represent functions in tables, right? Conversely, right, we can use information in tables to write functions, and we can evaluate functions using the tables. So for example, how well do our pets recall the fond memories we share with them, right? There's an urban legend that a goldfish has a memory of 3 seconds, but this is just a myth. Goldfish can remember up to 3 months, while the beta fish memory of is up to 5 months. And while a puppy's memory span is no longer than 30 seconds, the adult dog can remember for 5 minutes. This is a meager compared to a cat whose memory span lasts for 16 hours. The function that relates the type of pet to the duration of its memory span is more easily visualized with the use of the table. So here we go. You have the pet, puppy, adult dog, cat, goldfish, beta, and how long their memories last. Right? In hours, of course. Right? So Let's talk about this. So at times, evaluating a function in a table form may be more useful than using equations, right? Here, let us call a function p. The domain of the function is the type of pet, and the range is the real number representing the number of hours the pet's memory, or the pet's memory span, excuse me. We can evaluate the function p at the input value of goldfish. We would write the function p of goldfish is equal to 2,160. Notice that to evaluate the function in table form, we identified the input value and the corresponding output value from the pertinent row of the table. The tabular form of the function p seems ideally suited to this function, more so than writing in a paragraph or function form. All right. So that's that. Long story short, I'm going to ask you, give me the function of cat, right? And you just tell me the y value next to it, 16. That's it in a nutshell. All right. That's also on your homework. So given a function represented, excuse me, by a table, identify specific output and input values, right? So this is how we're going to do it. First, you're going to find the given input in the row or column of the input values. Step 2, identify the corresponding output value paired with that input value. Step 3, find the given output values in the row or column of the output values, noting every time that output values appear. And step 4, identify the input values corresponding to the given output value. That's it. So when I give you a table and I ask you, like, all right, given this input, what is the corresponding answer, the y value, just tell me back it. That's it. You know? It's on the homework. You'll see. And it's as simple as you might think it is. For example, let's take a look at this. So it says using table 11, which is that table right there, right? For question A, evaluate G of 3. What's the answer? Do this one. So I heard someone say 7. Good job. How'd you get that? 3 and 3 is right here, and it goes to 7. Very good. All right. A little bit harder. What's N?
2. 4.
4 and 2. Very good. Very good. All right. I have 2 different inputs that's going to the same output. All right.
Where's the,
Right here. All right. They both equal 6, but I have 2 inputs, 2 and 4. Right. Mhm. All right. Let's see if we really got it. No want no cheating. What's the answer? What is it? Very good. I'm impressed. I'm not gonna lie. Y'all probably halfway done with your homework by now. That's all good. I mean, you got your phone.
Nah, don't worry. I don't know if my login isn't the same as the old
It is first name, not last name, but the link is different now. Link
one.
is
But strict web work.
uh,
Of some,
I don't know. 2025?
yes.
Okay.
Hold on.
Or just go on Brightspace. Just click the link on Brightspace.
Yeah.
All right, so finding function values from a graph. Evaluating a function using a graph also requires finding the corresponding output value for a given input value. Only in this case, we find the output value by looking at the graph. So solving a function equation using a graph requires finding all instances of the given output value on the graph and observing the corresponding input values. All right. So let's take a look.
What would domain directory be?
Mhm. So main is the X value, range is the Y value.
I don't know, I meant like the solving.
Yeah. So real quick, I need a graph for this. Just give me 1 second. So let's say we have this graph right here, right? I want to evaluate f of 2. So when my X value, f of 2, right? My X value is 2. So here goes 2 right here. I just want to go up to where my Y value is. Hold on. Let me change my colors real quick. I'm gonna do pink. My fault. Sorry about that real quick. Let's feel like it'll pop, right? So my X value is 2 right there, right? So I'm gonna go up to the graph, which is right here, right? And I want that corresponding Y value, right? So f of 2 is what? 1, and that's it. All right. A little bit of a reverse now, right? Part B. Not working. Are you freezing on me? Whatever. B is f of x is equal to 4, right? So let me just erase this real quick. Let me look at where 4 is. It's right here, right? But it corresponds to 2 points on the graph. So what's the answer for this? -1 and 3. I'm just gonna say and. Make it easy. All right, those are my answers. I think in WebWord, you'd probably put like -1, 3 to separate them. But for us, I'm just gonna say and. Questions on this? You good? All right. Don't know why we freezing. Okay. So same graph. Solve f of 1. Now I really need another color. Come here. Where's orange? Here we go. So I want f of 1. Good. So when the y value is 1, the x value is 0. Particularly x equals 0, right? Okay. Questions on that, or are we good? It would also be 2. Good. It would also be 2. Why? Good. So when x is 0, it's 1. And when x is 2, it's 1. All right. Questions on that? Good. All right. So now let's take it up a notch. I mentioned something earlier about this. Let's really define it now. Determining whether a function is one-to-one. All right. Some functions have a given output value that corresponds to 2 or more input values, right? So for example, in the stock chart shown in the figure at the beginning of this chapter, the stock price was 1,000 on 5 different dates. We didn't talk about that, but y'all get the idea. However, some functions, right, have only one input value for each output value, as well as having only one output for each input. So we call these functions one-to-one functions. An example, consider a school that uses only letter grades and decimal equivalents as listed below, right? So you see how each input is different, each output is different, right? This is the one-to-one function, right, that we mentioned before. But this is it in like table form, right? So elaborate on this a little bit. So this grading system represents a one-to-one function because each letter input yields one particular grade point average output, and each grade point average corresponds to one input letter. To visualize this concept, let's look again at the two simple functions sketched in figure 1 and A and B. The function in part A shows a relationship that is not a one-to-one function because inputs Q and R both give output N. The function in part B shows a relationship that's one-to-one because each input is associated with a single output. So let me bring that up real quick. This is the figure we're talking about with the circles again. So as I was saying, that middle one, right? That middle relation right there is a one-to-one, right? Because each input corresponds to its own output and vice versa. All right. Questions on this? We good? So real quick, hit y'all with a quick definition. So one-to-one function. A one-to-one function is a function in which each output value corresponds to exactly one input value. All right. Each output is corresponding to one input. Look at an example real quick. So determining whether a relationship is a one-to-one function is the area of a circle, right? Area for circle. I believe that's pi r squared, right? Right, so is the area of a circle a function of its radius? If yes, is that function one-to-one? All right. So yeah, I can solve for area from this equation, right? Area is equal to pi r squared. Could also see it written like this. I don't need that part, but so yeah, that's a function, right? Is it 1-to-1? All right. So if it's 1-to-1, every area that I have or could get has to correspond to its own unique radius. All right. So long story short, can I solve for the radius? Right? Let's try. And then I have area over pi is equal to r squared, square root this, square root this. So I am going to get r is equal to plus or minus the square root of the area over pi, right? So I'm going to have two different inputs corresponding to one output, which is the area, all right? So nah, that wouldn't be 1-to-1. All right. Let's look at another example. Let's think through each one of these. It's a little bit challenging right here, this one. Is a balance a function of a bank account number? Is a balance a function of a bank account number? No? Why? Can two different bank account numbers have the same balance?
Yeah.
Okay. All right. So I would say it is a function. All right. Um, is a bank account number a function of the balance?
No.
No.
I think my bank account number doesn't, affect, it doesn't, by itself, doesn't influence the amount of money that's in the account. That goes
Right.
to my bank, account, what, as me, and $1 billion in my bank account.
Right.
Each one.
Right. All right. Is it 1-to-1? The bank account number with the balance. It's not. Because, like, for example, like your bank account, I know Ronnie's bank account, they both got $1 million in their bank account, you know? But the thing is though, right? They have two different bank account numbers. You know? It's not though, because y'all have the same balance.
They're the same.
Oh,
Yeah. Right, but different accounts. Yeah. Yeah. Right. Mhm. That's what it is. Yeah. Interesting concept, right? Let's take a look at another example. Oops, all right, that's good. So evaluate the following. If each percent grade earned in a course translates to one letter grade, is the letter grade a function of the percent grade? Is it?
In the output, um,
I would say yeah, it is. So like if you get 4.0, that's A,
and
like 3.0 would be, yeah, that was another table, right? But let me ask you this question though. Is it 1-to-1?
Yes.
It is, right? Because each percent grade is corresponding to a particular letter grade.
As Well, A, actually,
Right.
extension A should be from 95.
But forget the range though. Right? If it was just the 4.0, then that would be 1-to-1. You know? But you're right. If there was a range there, that changes the conversation, right? If I say from 90 to 95, wait, what was it again? No, from 95 to like 100 would be like a, right? So that's a range. That wouldn't be 1-to-1, right? That's like saying there's two different inputs right there, right? So- Yep.
So it was more, it was more.
Right. You know,
Okay.
interesting concept. Yeah. That's not on your homework. That's just for y'all to think, by the way. Mhm. The homework's actually like really, really easy. So let's talk about what you mentioned before, the vertical line test. Not gonna lie, that's my favorite right here. So using the vertical line test, as we have seen in some examples above, we can represent a function using a graph. Graph display a great many input/output pairs in a small space. The visual information they provide often makes relationships easier to understand. By convention, graphs are typically constructed with the input values along the horizontal axis, right? And the output values along the vertical axis. The most common graph names the input value x and the output value y. And we say y is a function of x or y equals f of x when the function is named f. The graph of the function is a set of all points x comma y in the plane that satisfies y equals f of x. If the function is defined for only a few input values, then the graph of the function is only a few points, where the x-coordinate of each point is the input value, and the y-coordinate of each point is the corresponding output value. So for example, the black dots on the graph, which I'm going to show you, tells us that f of 0 is equal to 2, f of 6 is equal to 1. However, the set of all points x comma y satisfying y equals f of x is a curve, and then the curve includes 0, 2, 6, 1 because the curve passes through these points. So let's take a look at that curve real quick. 1 second. Boom. Here we go. That's what we're talking about right here. Right? So f of 0 is equal to 2. That's going to be this point right here. And we can say that this is 0 comma 2. Right? And f of 6 is equal to 1. That's going to be this point right here. And we're going to call that 6 comma 1. And that's it. Questions on this? Good? All right.
And then you put there. Yeah, like, 6, 6 for 1. And I say, like,
Yeah.
I have another number that brings me into that saying
Mm.
6 candle.
Right.
The 4th of July will be passing 2 points.
Exactly. Exactly. That's it.
Where they
So-
just like, I'm looking at like data set,
Mm-hmm.
I'm like mentally drawn with 5.
Mm-hmm.
Somehow I need to like loop around.
Exactly. Then it's not going to work. So let's take a look at what you're describing. Check this out. So this is called the vertical line test, right? It can be used to determine whether a graph represents a function. If we can draw any vertical line that intersects a graph more than once, then the graph does not define a function because a function has only one output value for each input value. So the first one, right? We have this funny looking curve right here, right? We draw a vertical line through it. It cuts through it only at one point. That's a function, right? But I have this sideward looking curve right here, right? I draw a vertical line through it, it's cutting through two different points, right? So one x value is corresponding to two different y values. That's not a function, right? Last example, I have a ellipse. Is that what you call this? An egg, whatever, right? You draw a vertical line going through it, it's gonna touch at two different points, right? So because it's touching at two different points, this is not a function. All right. Questions on this one? Make sense? All right. Let me give y'all a little sauce real quick. Little how to. So given a graph, use the vertical line test to determine if the graph represents a function. Step one, inspect the graph to see if any vertical line drawn would intersect the curve more than once. Step two, if there is any such line, determine that the graph does not represent a function. All right, that's it. So you draw a straight line through it, vertical line, excuse me. If it cuts the graph in more than one place, not a function. That's simple. So for example, help me out with these. All right. Using the vertical line test. A, is it a function? Yes, very good. B, is it a function?
Yes.
C, is it a function? Why? Okay. It's gonna touch it twice, right? The vertical line that goes through it. All right. So we good? This makes sense? All right. Two, 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 two. Help me out with this. Function or not a function? Very good. All right, let's keep going. Using the horizontal line test. All right. So once we have determined that a graph defines a function, an easy way to determine if it is a one-to-one function is to use the horizontal line test. So you draw a horizontal line through the graph. If any horizontal line intersects the graph more than once, then the graph does not represent a one-to-one function. All right? Real simple. Just draw a horizontal line through it. Give y'all a little bit of sauce before we look at an example. So how to? So given that a graph of a function, right, use the horizontal line test to determine if the graph represents a one-to-one function. Inspect the graph to see if any horizontal line drawn would intersect the curve more than once. If there is any such line, determine that the function is not one-to-one. Very simple. So you draw a horizontal line. If it's cutting the graph twice, it's not one-to-one. It could still be a function, it's just not one-to-one. That's all. So my next question. One second. It worked. Hey, all right. So my next question, right? Is it a function? And if it is a function, is it one-to-one? A. So it's a function. Is it one-to-one? Very good. B, is it a function? Is it one-to-one? Very good. C, is it a function? Okay. All right, very good. Is C one-to-one? Good. I'm impressed. I'm not gonna lie. Let's take a look at this. So we're identifying basic toolkit functions. So in this text, we'll be exploring functions, the shapes of their graphs, their unique characteristics, their algebraic formulas, and how to solve problems with them. When learning to read, we started with the alphabet, right? When learning to do arithmetic, we started with numbers. When working with functions, it is similarly helpful to have a base set of building blocks elements, right? We call our toolkit functions, which form a set of basic name functions for which we know the graph, the formula, and special properties. Some of these functions are programmed to individual buttons on many calculators. For these definitions, we will use X as the input variable and Y as the output variable, right? And then we will see these toolkit functions, combinations of toolkit functions, their graphs, and their transformations frequently throughout the text. It will be very helpful if we can recognize these toolkit functions and their features quickly by name, formula, graph, and basic table properties, right? So let me show y'all the basic toolkit functions that we're talking about. This is really cool. Y'all gonna get a kick out of this. So the first one is a constant, all right? So it's our toolkit functions right here, right? So when we have a constant, that means that the function f of x is equal to c, where c is a constant number. I don't care what it is. Could be 3, 4, 5. This case is 2, right? That's going to be a horizontal line going across the graph, right? No matter what x value you give me, the y value will always be 2. That's a constant. All right. Questions on this one? Make sense? All right. So I'm going to show you an identity one. This one's pretty cool. So identity, this is f of x is equal to y. Sometimes this is called y equals x, right? It's a line that goes through the origin, right? Very simply, whatever number you give me for x, that's the number it is for y, right? So 1, 1, 3, 3, -5, -5, etc. All right. Horizontal line, not horizontal, excuse me, diagonal line going through the origin. Questions on this? All right. Let's look at some more. Now, we saw this a little bit earlier, but we didn't elaborate about it, so let's talk about it now. This is the absolute value function right here. So this is like f of x is equal to absolute value of x. That's what these bars right here represent, absolute value, right? What that means, or what the absolute value is, just give you a quick definition, right? It's how many units a number is from 0, right? For example, if I say, what is the absolute value of 5? 5 is 5 units from 0, so the answer is 5. If I say, what is the absolute value of -12? Right, it's 12 because -12 is 12 units away from 0, right? This is the graph of the absolute value. Looks like a V, all right? So whatever number you give me, could be positive or negative for the input, the output is gonna be that same number, but positive. All right? Let's look at something else. Now I know everybody in here knows this next one. This is the famous one right here. All right, it's the quadratic right here, right? This is y equals x squared right here. Looks like a u, right? That's the graph, right? So whatever input value I give you, you're gonna square it. So if I give you like 3, 3 squared is 9, boom. There you go. All right? Questions on this one? I feel like everybody got this one. All right. That's not the last one though. We got some more. This one is called the cubic. So this is y equals x cubed, right? So whatever input value you give me, I'm gonna give you the output is gonna be that same number raised to the third power, right? And that's it. It looks like a curved line going through the origin, right? This is the cube, all right? All right. I feel like everybody knew these, but y'all might not have known these next ones coming up. All right. About to give y'all the reciprocal now. So the reciprocal is like y equals 1 over x. This is how the graph looks, right? So we're in the first quadrant, just kind of curving down from there, and also in the third quadrant, curving. All right. So whatever input value that you give is going to be 1 divided by that number. So if it was like 2, it'd be like 1 over 2. If it was 3, it'd be like 1 over 3, etc. This is what the graph looks like. All right. That's the reciprocal. This next one, same idea, reciprocal, but this time we're going to square it. So this is the reciprocal squared. Or y equals 1 over x squared. This is the way that graph looks, right? Both of them going towards the y-axis and then to infinity right there. Right? Go on both sides, it's going close to the x-axis, but never actually touching it. All right. This next one was definitely a new one for me back in the day. This is the square root. So this is y is equal to the square root of x. This is how the graph looks. Start off in the origin, goes off, right? Remember it's illegal for us to take the square root of a negative number. That's why there's no negative, there's no bottom part to this, right? Like when I say bottom part, I mean below the x-axis. There's no graph. That's what I meant. All right. And then check this out now. So this is the cube root. Right? So y equals the cube root of x. This is the way that graph looks. So it looks like the x cube, but just turned sideways. All right? And that's it. So those are your basic toolkit functions. Once you know those, you're good to go. All right? You can rewatch this in the video if you want to go through them again. No problem. So this next topic is thanks to Ronnie. All right, we're gonna be finding the domain of a function defined by an equation, right? So in functions and functions notation, we were introduced to the concept of domain and range. In this section, we will practice determining domain and ranges for specific functions. Keep in mind that in determining domain and ranges, we need to consider what is physically possible or meaningful in real world examples, such as ticket sales and year in horror movie example above, right? We also need to consider what is mathematically permitted. For example, we cannot include any input value that leads us to take an even root of a negative number if the domain and range consist of real numbers or a function expressed as a formula. We cannot include any input value in the domain that would lead us to divide by zero. Blah, blah, blah. Long story short, it's illegal to divide by zero. It's illegal to take the square root of a negative number. Just remember that. All right. Everything else is fine.
Okay.
That's fine. We'll get to that. But I do remember we did that in 28. So we can visualize a domain as a holding area that contains raw materials for a function machine, and the range as another holding area for the machine's products, right? So domain, think of that as your inputs, your ingredients. Function is the machine, right? The range is going to be all of the output. That's your storage for the company. Think of it like that. All right. But it is the same concept of X and Y. All right, so we can write the domain and range in interval notation, which uses values within brackets to describe a set number. And in interval notation, we use a square bracket when the set includes the endpoint. That's important. And a parentheses to indicate that the endpoint is either not included or the interval is unbounded. For example, if a person has $100 to spend, they would need to express the interval that is more than 0 and less than or equal to 100 and write 0 comma or open parentheses 0 comma 100 close bracket, right? We will need to discuss interval notation in greater detail later. Let's turn our attention to finding the domain of a function whose equation is provided. Oftentimes, finding the domain of such functions involves remembering three different forms. First, if the function has no denominator or an odd root, consider whether the domain could be all real numbers. Second, if the denominator in the function's equation exclude values in the domain that force the denominator to be 0. Third, if there is an even root, consider in excluding values that would make the radicand negative, right? The inside part. Before we begin, let's review the conventions of interval notation. The smallest term from the interval is written first, so we always go from smallest to largest. The largest term in the interval is written second, followed by a comma. Parentheses are used to signify that the endpoints are not included, called exclusive, right? Brackets, open bracket, close bracket, are used to indicate that the endpoints is included, and this is called inclusive. All right. Questions on this? All right, domain and range, domain and range.
Like it's, negative, you know,
Inclusive. Like that number is in the set. All right. But parentheses is not. Yeah. Parentheses, like I'm just going up to that number, but I'm not including that number in the conversation. Yeah. Give you guys a little graph real quick to take a look at. All right. So we have our inequality. Let's say that x is greater than a. That means that I want from a to infinity. That's how you would write an interval notation. So open parentheses a, close parentheses, infinity, right? On a number line, it looks like this. You have a, right? This was gonna be here, and we're gonna go all the way out to infinity, right? So x is greater than a, that's the description of it. Let's look at the next one. X is less than a, right? So that means I want to go from negative infinity up to a, right? So on the graph, it's gonna look like that. From negative infinity up to the a, x is less than a. Next, we have x is greater than or equal to a, right? So that means I'm including a now up to infinity, right? And then on the graph, it looks like that, bracket on top of the a going to infinity, x is greater than or equal to a. Then you have x is less than or equal to a. This is gonna be negative infinity to a. It's gonna go from negative infinity, but I'm gonna end it with the closed bracket, right? X is less than or equal to a. Last but not least, we have a is less than x, which is less than b. That's gonna be from a to b in parentheses, bless you. Right, and then that's how it's gonna look on the graph, open parentheses, shade in the middle, close parentheses, x is strictly between whatever a and b is, all right? And then three more. All right. Then we're gonna have a is less than x, which is less than b. So that means I'm not gonna include a, but I'm gonna include b in this one, right? So that's gonna be open parentheses a, b close bracket. That's how it look in the graph, right? I like the way that these graphs are done with the parenthesis and the brackets. Right? If you remember back in the day, we used to do open circle, closed circle. So the open circle, right, is not included. The closed circle was included. Right? Same idea here. All right. Last but not least, I have a less than or equal to x, which is less than or equal to b. Right? So that means that a is included, b is included, two brackets. Questions on this?
Okay. Yeah, but, you must look that,
Up and right, yeah. Hmm?
Yeah.
Yeah.
like we know, I said A is less than X,
Mhm.
less than equal to B,
Mhm.
it's less than equal to B, so you can go into one, starting from generally picking up
Right.
is B.
Right.
So, okay, B is two,
Mhm.
two is the bracket, because two is the definitive number, no.
Right.
Anything before or after that is technically.
Doesn't work, right? Yeah, that's true. Go ahead, what was your question? For which one?
The top.
Top, I'll go right here. X is less than or equal to a. So I want all of the numbers that are smaller than a. But you know, numbers don't end kind of nonsense, so that's why it's negative infinity. Yeah. Let's see. Are we good? All right. Closed circle is the bracket. Yeah. Open circle is the parentheses. All right, let's take a look at this example. Finding the domain of a function as a set of ordered pairs, right? So this says find the domain of the following function. So we have curly bracket set, 2 comma 10, 3 comma 10, 4 comma 20, 5 comma 30, 6 comma 40. The domain is all of the x values that are here, right? So you can literally just list them out. So 2, 3, 4, 5, 6. And that's it. Questions on this? Anybody? All right, so domain is all of the X values. So you guys try. Tell me what the answer is. Good. Mhm. Very good. You just put them in like a little bracket, make it pretty, and that's it. All right. I don't think you need the bracket for the curly brace for the homework. I think you're just separated by a comma. You should be good for this one. Give you guys a little bit of sauce real quick. So given a function written in equation form, find the domain. So identify the input values, identify any restrictions. Step 2, identify any restrictions on the input and exclude those values from the domain. Step 3, write the domain in interval form if possible. And that's it. Mhm. Identify the input values and write the inputs. What about this example? So I have f of x is equal to x squared minus 1. What's the domain?
We gotta make the value something, right?
Hmm?
Like 2 squared, like I put any X value, but after the one.
That's the answer. I could put any x value, right? So the domain here is all real numbers, or you could say negative infinity to infinity, right? I think how we say infinity in WebWork. I think it's INF. Like literally just type that INF and it should be there. But they have this new like math feature on WebWork where you could just like click it on the side and it just comes up real nice and handy. You know? Yeah, yeah, yeah.
Mine's not working.
It's not working?
It's first name, last name for the username and password.
Yeah, yeah, yeah.
No space, nothing.
No space, nothing.
Sure.
If it's not working though, like can y'all like send me an email, let me know. You know, like if you guys had trouble tonight getting into web work and stuff. That being said, what's the domain for this? Same thing, right? There's no X value that is illegal here, so domain is negative infinity to infinity. All right. Questions on this? Good.
But they,
Right.
there. Well,
What do you mean by like if it was y equals 7, for example?
standard,
Mhm.
value that we don't talk.
Right,
Maybe any value.
right. But it depends on the function. Some functions have X values that are illegal, all right? And the two illegal things is we cannot divide by 0 and we cannot take the square root of a negative number, all right? Everything else is legal. Just give y'all some good notes real quick on this one. So given a function written in the in an equation form that includes a fraction, find the domain. So step one, you want to identify the input values. Step two, you want to identify any restrictions on the input. If there is a denominator in the function's formula, set the denominator equal to 0 and solve for x. If the function's formula contains an even root, set the radicand greater than or equal to 0 and then solve, right? Write the domain in interval form, excuse me, making sure to exclude any restricted values from the domain. All right? Let's take a look. So for example, so finding the domain of a function involving a denominator. Find the domain of the function f of x is equal to x plus 1 divided by 2 minus x. So what would this be? What's the domain? What is it? Say it again? No.
Yeah, it said 0, right?
Set the denominator equal to 0 and then solve for it, right? So over here, just so you can all see, this is f of x is equal to x plus 1 over 2 minus x. Set the denominator equal to 0, 2 minus x equals 0. Solve for x. This gives me what? X equals 2. So what's that telling me? All numbers I could plug in here except 2. Because if I plug in 2, what happens to the denominator? It becomes 0, and that's illegal. I can't divide by 0, right? So your domain here, right, is going to be from negative infinity, right, up to 2. We're going to union that with 2 up to infinity, right? So I can plug in all numbers except 2. 2 will ruin us. All right. Questions, anybody?
All of them that is together,
Yeah.
I don't look at negative two.
As long as you put it together like this. Yeah. And we have the union right there.
So we combine that one, what the student do, we put an absolute value on.
No, that's different. I know what you're saying. That's something else. Yeah. That won't be on your homework. This stuff, this interval stuff will be on there. Yeah.
The U in between is putting when it said it's and.
Right. It's like I'm connecting them together. Yeah. What's the domain here? What's the domain there? Tell me what to do.
0.
Set the denominator equal to 0. So 2x minus 1 equals 0. What's the answer for x? Mm-hmm. Divided by 2, right? So x equals 1/2. So what does that mean? What's the domain? Everything but 1/2, right? So domain is negative infinity to half union half to infinity.
And the fact that that'd be right.
Because it's not included. Yeah. Actually, if it was included, I wouldn't even need the union nonsense. It would be everything, right? Questions on this? The same way. Open parentheses, negative infinity. Infinity is INF, I believe, but you can just click it on the side kind of thing. And then just capital U. Right for the middle. Yeah. And that's it. And for like the half, it's just 1 divided by 2. That's all. Questions? Good. All right. Let's keep moving. So here's that other situation. So given a function written in equation form, including an even root, find the domain, right? So step 1, you want to identify the input values. Step 2, since there is an even root, exclude any real numbers that result in a negative number in the radicand. Set the radicand greater than or equal to 0 to solve for x. Step 3, the solutions are the domain of the function. If possible, write the answer in interval form. Questions? Are we good? All right, let's keep going. Let's look at this example. So finding the domain of a function with an even root, we have f of x is equal to the square root of 7 minus x. What is the domain? What should I do here? Tell me. Very good. And what do I do after that? You add what, the x? Okay. So we have 7 is equal to x, right? Okay. So what numbers can I plug into this? Well, what is the domain? Uh-huh. 7 is in, right? So from 7 to what? 7 to positive infinity. Like this? I'm sorry, hold on. Like this? No. So the domain here is actually the reverse. It's negative infinity to 7 with the bracket. Right? Why is that? I can't take, right, the square root of a negative number, right? If I make it all positive, it's going to become negative as it grows, right? So really what we needed to do, if we wanted to avoid that mistake, right, is do 7 minus x greater than or equal to 0, right? And then when you solve for x, you'll see it. So this is what? This is 7 greater than or equal to x, or read it in reverse, x less than or equal to 7. And then that's it. Questions on this, anybody?
Well,
Let's see.
why is it negative? It's not positive.
Because I need the number underneath the radicand, the 7 minus x, that has to be positive, right? If it's negative, it's not going to work. I can't take the square root of a negative number.
Yes, so why would
Yeah. Put a domain, at least. Yeah.
but you have to start that you have to be 0, 1.
This one starts at the 7 because of the 7 minus x. I know what you're saying, though.
So
Yeah, I got you, I got you. Infinity. Um, to be honest with you, I just copied from up here. In yellow.
Yeah,
Set the radicand greater than or equal to 0. Yeah. But also I know that the rule is I can't take the square root of a negative number. So in my head, if I didn't know to do this, I would go straight to a number line. I already know what the deal with 7 is, right? 7's included. But I would test a number bigger than 7, call it 8, and a number smaller than 7, let's call it 0. Right? If I plug in 8, right, this becomes negative, and if I plug in 0, this becomes positive. So I know from right here it has to be everything going this way. So we good?
yeah.
All right, let's keep moving. Feel like y'all get the idea. Let me just make a special note real quick. So for this question, can there be functions in which the domain and range do not intersect at all? Right? Yes. So for example, f of x is equal to negative 1 divided by the square root of x has a set of all positive real numbers as its domain, but the set of all negative real numbers as its range. So as a more extreme example, the function's input and output can be completely different according, can be completely different categories. For example, names of weekdays as inputs and numbers as outputs as on an attendance sheet, chart, excuse me. In such case, the domain and range have no elements in common. All right.
So,
I'm sorry.
but that looks like.
Visually, 1 over square root of x. So you know what square root of x looks like. It's just that from the origin going that way, right? So imagine it's negative, so it's flipped backwards, right? And then 1 over, so in the third quadrant, like that. Yeah. That's coming. That's like Wednesday or Thursday's lesson. So using notations to simplify domain and range. In the previous examples, we used inequalities and lists to describe the domain of functions. We can also use inequalities or other statements that might define sets of values or data to describe the behavior of variables in set builder notation. So for example, you have x such that 10 is less than or equal to x, which is less than 30. Describes the behavior of x in set builder notation. The braces is read as the set of, and the vertical bar is read as such that. So we would read x such that 10 is less than or equal to x, which is less than 10, as the set of x values such that 10 is less than or equal to x and x is less than 30. All right. Figure 5 compares inequality set builder notation and interval notation. So here you go. Let's make that a little bit bigger. All right, so we're gonna go from 5 to 10. Open circle, not included. Closed circle, included. So interval notation, this is 5 less than h less than or equal to 10. Set builder notation is h such that 5 is less than h, which is less than or equal to 10. Interval notation, which is the real one I'm gonna be asking you for. We're going from 5, comma to 10. 10 is included. That's it. Another example, again, closed circle, included, open circle, not included, right? We're going from 5 less than or equal to x less than 10, or h, such that 5 is less than or equal to h, which is less than 10. And then we have our interval notation, which is 5, comma 10. 5 is included. All right?
You know, it's not further notation, that like, after that.
It can be. It can be. I mean, if you want to do it on your paper or your homework, go ahead. I think the homework wants the interval notation, and I would prefer the interval notations. That's the main thing.
I don't really see, like.
Yeah.
H, the value of H is
Mhm.
5, less than.
Less than
which
H.
less than equal to 10.
Right. A little bit different, but reversed. Let's see. Next one, we have 5 less than H less than 10. Just H such that 5 is less than H less than 10. That's 5 and 10 with parentheses not included. All right. You have H less than 10, that's everything to the left, negative infinity up to 10. H greater than or equal to 10, so that's bracket 10 to infinity, etc. All real numbers, it's the whole number line, negative infinity to positive infinity. That's it. All right.
So, that is, that forward.
Yes. Yeah. So, trying to see what else I could say. Let me give you like 2 more things, then we could call it at that. Just 2 more things. All right. You know, I always got to give y'all the sauce. All right. So, given a line graph, describe the set of values using interval notation, right? This is how to do it. Step 1, identify the interval to be included in the set by determining where the heavy lines overlap the real line. Step 2, at the left endpoint of the interval, use the bracket, right? With each endpoint to be included in the set, solid dot, or for the parentheses, right? For each excluded endpoint, open dot. At the right end of each interval, use the bracket, right? With each endpoint to be included in the set, filled out dot or parentheses for the excluded endpoint, open dot. Use the union symbol, the U, to combine all the intervals into one set. All right. That was basic stuff. One last thing. One quick last thing, So this is finding the domain and the range from the graph, right? So another way to identify domain and range of functions is by using graphs. Because the domain refers to the set of all possible input values, the domain of the graph consists of all input values shown on the x-axis. The range is the set of possible output values, which are shown on the y-axis, right? Keep in mind that if a graph continues beyond the portion of the graph, we can see that the domain and range will be greater than the visible numbers. That's the infinity, all right? So real quick, let me just show you this one graph and then we call it at that. This is just going to sum up everything, all right? So if I have a graph here, right? This nice looking blue, dark blue line, right? The domain is all of the x values that the function exists at, right? So for here, my domain will be -5. Is that bracket or parenthesis?
Oh.
No, right here, going this way. -5 up to what? No. -5 to, sorry about that, to infinity. It keeps going on, all right? This would be my domain. The range, however, is all of the y values, right? Range is just the y values, right? So I'm looking over here now, right? For the range values going all the way down, right? So this is going to be from what?
Five.
So I heard negative infinity up into 5 included, right? That's the range. All right. You will see questions like this on your homework, right? Where they just gonna ask you, they give you a graph and they tell me, just tell me what the domain is, tell me what the range is. And that's it. All right, y'all should be good to go. Y'all have enough information. Huh?
Doing tennis?
Yes, I forgot to do that.
Yeah.
Yes, homework is there. You know what? Everybody just send me an email for attendance today. 'Cause I kept y'all a little bit past time. Yeah. And also in the email, include like if you guys can get into web work or if you're having trouble. All right, just want to make sure. All right. See you, man.
Like.
I mean, just give me the 100. Just give me the 100. It grades it for you. Yeah, you can try it as many times as you want, no penalty.
Yeah.
Just give me 100. Yeah. Yeah. Yeah.
And
Just send me an email with it.
okay, it's literally just about the cheat sheet.
Yeah.
I really a lot of people use it.
Yeah. Yeah.
Just not wanted to make sure.
Yeah. You can use it for your homework too.
I got
Yeah.
Sunday evening.
Yeah. All right, you're welcome. You're welcome.
Thinking about this for a while.
Yeah, what you thinking about?
It may or may not be, but it's fine.
Nah, you good. You welcome. You too.
So the reason for it, I didn't take Ferguson for this class.
You didn't. Right, because you took 23.
So I didn't take.
Hold on 1 second.